So today I'm going to be talking about spontaneity and the second law of thermodynamics, Dr. Kildea style. So I got my iPad here and my Apple Pencil that's charged, of course. So when we talk about spontaneity, spontaneity means that a process will happen without having to put any work or effort into it. So this can be examples like free gas expansion, mixing of gases, and phase changes. So in the case of free gas expansion, we talk about when you have a gas, say in like a closed container, and then you say open the container, then all the gases will diffuse into the air. So that happens spontaneously because there's not really any work being put into it. And this is also the case with phase changes. So if you have an ice cube and you just let it sit out there at room temperature, then eventually it will melt. And this also happens spontaneously. So spontaneity is measured in entropy, and entropy is denoted by delta S. And delta S is a state function, so that means that we can look at the initial and final states to calculate it, and it doesn't really matter about the path it takes to get from point A to point B. So we can demonstrate the state function, or we can demonstrate that entropy is a state function with Carnot cycle. So the Carnot cycle is a series of 4 steps. So, and it can also be demonstrated on a PV diagram. Okay, so there are 4 steps to the Carnot cycle, and if we look at it on the PV diagram, it looks like this. So going from state 1 to state 2 is an isothermal expansion, and then from state 2 to 3 is an adiabatic expansion, and then 3 to 4 is an isothermal compression, and then going back from step 4 to step 1 to the original state is an adiabatic compression. See that the Carnot cycle is important because it shows us that entropy is a state function. And the idea behind the Carnot cycle is that you have a hot reservoir and a cold reservoir, and as you draw heat from that hot reservoir to the cold reservoir, you can get work out of that, and which is useful because then you can use this flow of heat from the hot reservoir to the cold reservoir to get work so that you can go and use that work for other processes. For reversible spontaneous processes, that can be demonstrated with the Carnot cycle or just plotting it on a PV diagram. But for irreversible spontaneous processes, once that process has occurred, we can't really go back to its initial state. So then for the spontaneous process, delta S is positive, so above 0. So the entropy has increased, and since it's irreversible, we can't go back. So the entropy is there forever. So this brings us to the second law of thermodynamics, where it states that the entropy of the universe is always greater than 0. So the entropy of the universe, you can calculate it by adding the entropy of the system you're studying plus the entropy of its surroundings. And since we always have irreversible processes, the entropy of the universe is always going to be increasing. So to put this into perspective, we take example for burning a log. So if you burn a log, you get ashes and gases released from it into the atmosphere. And there's no way, it's pretty impossible to go back to the form of a log. So since this process is 1, spontaneous, and it's 2, irreversible, and we always have processes like this in the universe, then therefore we have the second law of thermodynamics, which means that the entropy of the universe is always increasing.